In your calculus career so far, you've already seen a couple fundamental theorems of calculus. Whether you realize it or not, all of these theorems take a certain form. They all look like the integral over some region of the derivative of something, and what that derivative means depends on the context. And these theorems state that this integral equals the integral over the boundary of that region of the thing. So again, in words, any kind of fundamental theorem of calculus says the integral of the derivative is the integral of the thing over the boundary. Now, I won't spend too much time talking about this, but just to show you what I mean, let's think about the fundamental theorems that you've seen so far. One of the fundamental theorems of calculus that you're already familiar with, and sit down, this is going to be a surprise, is the fundamental theorem of calculus. And I'm just talking about the regular one that you learn in kindergarten that says if you want to integrate a function from a to b, what do? You find an antiderivative and you plug in the endpoints and subtract. And it doesn't look like the form in the thought bubble, but I claim that it is, up to some different notation. The region we're integrating over here is an interval. It's just an interval from a to b. So on the left-hand side here, we do have an integral over the region ab of little f. Well, that's capital F prime. So there's the derivative of something. And then on the right-hand side, the boundary of this region a to b is the 2-point set a comma b. The boundary of an interval is just its endpoints. And again, don't worry too much about this. This is introducing some wacky notation just for the sake of an analogy. But you can think about f of b minus f of a as some kind of oriented integral over the 2-point set a, b. I could go into this more, but I won't for now, so just trust me, it makes sense. And then the other fundamental theorem you've seen at this point is the fundamental theorem of conservative vector fields. This is pretty much the same statement as the fundamental theorem of calculus, just with an arbitrary curve rather than an interval. This fundamental theorem says that if you integrate a vector field along a curve, all you have to do is find a potential function and evaluate that at the endpoints, like in the prior case. And before, we could write this in the form in the thought bubble by saying, well, capital F here is the gradient of f. This is the derivative part. It looks like the gradient in this theorem. And then again, the boundary of a curve is just its endpoints. So the sum on the right is some sort of integral over the 2-point set a, b. Anyway, so far this has just been a bunch of meta mathematics, and it's an introduction to the topic of this video, which is Green's theorem. The whole point of this spiel that I just gave is that Green's theorem is another fundamental theorem of calculus, and it may not look like it, but it takes the exact same form. It's going to look like the thing that I wrote in the thought bubble. And to jump the gun a little bit, all of the other theorems we're going to come across, like Stokes' theorem and the divergence theorem, they will also take this same form. At the heart of it, all of these theorems say the same thing. But anyway, there's some details to fill in, so let me write down the statement of Green's theorem. It concerns a region in the plane. So in particular, for now, I'll just say let D be a bounded region in the plane. And suppose we have a vector field F defined on this domain D. Green's theorem says that the double integral over this region of the curl of the vector field is the same as the line integral of the vector field over the boundary of the region. To relate this to the thought bubble, the derivative here is the curl. And then indeed, it does in fact look like the integral over a region of the derivative of f. then we're equating that to the integral of the boundary of f. Now there are some other important remarks to make here. The first of which is, anytime we talk about a vector line integral, like on the right-hand side of this equation, we have to talk about the orientation of the curve. And right now I haven't said anything about the orientation. Also, just in case you haven't seen this yet, when I write this del symbol, like here, del d, this is the notation for boundary. That might seem a little weird because we use del for derivatives and stuff, but that's kind of exactly the point. The point of all this fundamental theorem stuff is that a boundary operation is somehow dual to taking a derivative. Anyway, so the important thing I was going to talk about is the orientation of this boundary curve. Given a region, the orientation of the boundary curve is determined by the region always being to the left of the curve. So if I had a blob like this, and I told you to stand on the curve and walk in some direction so that the red region was always to your left, which way would you walk? You would walk like this. In contrast, if you were to walk this way, if you looked to your left, you would not see the region. The region would be to your right. That's not what we want. So anyway, when you apply Green's theorem, this is how the orientation of the boundary is determined. Now, one more quick remark. It might be tempting to listen to me say that and think, oh, okay, so it's always counterclockwise. And I would say, no, be a little careful with that. I would stick to thinking about the region being to your left. There's a couple reasons for that, but one of them is maybe just an example that we could look at in possibly the next video. The last thing that I wanted to do before we look at some examples is to give you a little bit of intuition as to why this might be true, or one way to interpret what this theorem is saying. To do that, I want to remind you of a couple vague things. The first of which is that curl somehow measures microscopic circulation or microscopic rotation of the vector field. So the curl at a point is some measurement of how much the vector field is spinning kind of in this direction. So if I draw a bunch of little arrows on my picture here, little swirls, these little swirls represent the curl of the vector field. Again, that's vague, but whatever. The point is that curl measures microscopic circulation. On the other hand, a vector line integral measures macroscopic circulation of the vector field around the curve. Again, what does that mean precisely? I don't know anything about physics. To me, it doesn't mean anything precise. It's just a vague concept that when you compute a line integral, you're measuring how much the vector field is flowing with the curve. So if you compute a line integral around a closed curve, you're measuring some sort of circulation around that curve. With this language, what does Green's theorem say? On the left-hand side, we have the integral of the curl. In other words, we're adding up all of the microscopic circulation in the region. On the right-hand side, we have a line integral of f along the boundary. So that integral represents the macroscopic circulation around the boundary curve. So what Green's theorem is saying is that the sum of the microscopic circulation in the region is the same as the macroscopic circulation around the boundary. And to drive this point home, I want to draw a quick picture to demonstrate why this may be true. Now, this is just a picture, so don't read too much into it, but it's kind of fun and I think it gets to the idea. Suppose I draw a little square of green arrows, rotating counterclockwise. Something like this. I'm thinking about this little square of arrows as representing one of these little swooshes in the region D. In other words, this is somehow supposed to represent the curl. It's some sort of microscopic circulation around a point. So what if I take that microscopic circulation and I copy it a bunch of times and I generate a big region, like a 3x3 square of such things? Then you could think about this square as being the sum of a bunch of microscopic circulations. In other words, this picture would represent the double integral of the curl over this square. But notice that when I draw all of these squares next to each other, a lot of these arrows on the interior are going in opposite directions right next to each other. So if you think about curve arithmetic or vector addition, they kind of cancel each other out, whatever that would mean in this picture. So all of these vectors nullify each other, and what are we left with? The only things that survive are the ones on the boundary. We're left with a picture like this. And adding all these up represents exactly the macroscopic circulation around just the boundary. That's the line integral of f over the boundary of d. And Green's theorem is just the statement that these are the same thing. So like I said, this is just a metaphorical picture. Don't read too much into it, but it is a really pleasing thing to think about. And this is the kind of thing that Green's theorem is getting at. Okay, but with that, let's get some real hands-on practice with using the theorem. We'll start off with an easy example, and then we'll do something more interesting in the next one. But first, this one will be a relatively basic and straightforward application of Green's theorem. So I have a curve, C, and it's made up of three parts, C1, C2, and C3. C1 is the line segment from the point 0, 0 to the point 1, 2. C2 is the line segment from 1, 2 to 2, 0. And then C3 is the line segment from 2, 0 to 0, 0. So we'll draw that in a second. But we're also given a vector field f, x minus y and x plus y. And we're supposed to compute the integral of f along this curve. Before we do anything, let me just draw a picture really quick. We have the point 0, 0, 1, 2, and 2, 0. And the three components of the curve are just the line segments connecting all these points. But, and this is important, they're oriented specifically like this. So we travel in a big triangular loop, starting at the origin up to the point 1, 2, and then back. Now I bring this up a lot, but I know we're in the middle of a video about Green's theorem. But nothing in the problem says anything about Green's theorem. I'm going to pretend like I found this problem on the street and I can do anything I want to figure it out. And the first thing to consider is that, what are we supposed to do? We're just supposed to compute a line integral. Well, we know how to do that. If you want, you could just compute this directly. It'd be a little annoying just because you'd have to parameterize the three different segments. So it would take some writing, but you could do it. Really, the main annoyance is just the fact that you would have to parameterize three separate curves. So instead of doing that, we can try to think about something a little more clever to save ourselves some work. And again, before I start thinking about Green's theorem or whatever, I notice that this is a closed loop. Maybe f is conservative. If it is, this would be really easy. It's a closed loop, so the integral would be 0. So this is probably the first thing I would do. Let's check if f is conservative. In this case, we could do that by taking the curl, because I know that f is defined everywhere on R2, which is simply connected. So if we take the curl and we get 0, then boom, that tells us that f is conservative on all of R2. That's what I'll do. I'll take the curl. In the two-dimensional case, the curl is going to be the derivative of f2 with respect to x minus the derivative of f1 with respect to y. And this would be 1 minus -1, which is 2. And, okay, 2 is not 0. So therefore, f is not conservative. So that's okay. All that means is that we can't just immediately say that the integral will be 0. So instead, let's try Green's theorem. This seems like a reasonable thing to do just because we know that Green's theorem would let us relate the integral around the boundary of this triangle to a double integral over the interior. So the first thing I'll do is I'll color in the triangle and I'll give it a name. I'll call it D. I'll let D be the region contained by the curves. And let's think about what Green's theorem tells us. Now, one thing we have to be a little careful about here is the orientation of the boundary curve. Notice that C, the curve we actually care about, is traveling clockwise. In other words, when you walk along C, D, the blue triangle, is always to your right. But when we talk about Green's theorem, we always want the region to be on our left. So the orientation of C is opposite that of the orientation of the boundary of D. The boundary curve of D would actually be negative C. So when I use Green's theorem here, I could say that the integral of f over c, the thing that we care about, this is going to be negative the double integral of the curl over D. And again, this negative sign is here because of the boundary orientation. So I'll let you think about that for a second to make sure it makes sense. But then from here, it's easy. We computed the curl above, it's 2. So this double integral is just the negative double integral of 2. Well, when you factor out that 2, the double integral is just going to give you the area of D. But I did pretty well in elementary school, and I know how to compute an area of a triangle. It's going to be 1/2 base times height. So at the end of the day, we get negative 4. And we've showed that this line integral of f over c is negative 4 without doing really any calculus computation at all. Again, you could just compute it. It's probably not that hard. But this is extremely slick and very easy. The only thing to be careful about really is just the boundary orientation nonsense. Now we'll do something a little more involved. In this example, we're given a vector field, 2x over x squared plus y squared, and then y over x squared plus y squared. And we're given a curve C. This is the curve defined by y equals 2 minus 2x to the fourth for x between negative 1 and 1. The orientation is from left to right. And just like before, we're just supposed to evaluate the line integral of f over this curve. So a couple remarks before we get going. Like I just talked about in the previous example, nothing in this problem says anything about Green's theorem. We can do whatever we want. And in particular, if you want, you could just try to evaluate it directly. You could parameterize the curve, plug it into the vector field, and go from there. That's not what we're going to do, but you could try. Now, typically, I don't think this is a great idea in scenarios like this, because when you have something like x to the fourth interacting with like x squared plus y squared stuff, usually they don't play well together. So my gut reaction when I look at something like this is I probably don't want to try to do this directly. I probably want to come up with something more clever. And that's what we'll do, but I will say that if you try to evaluate it directly, it's actually not that bad, and using some of the same tricks that we're about to do in this solution, you can get the answer relatively easily. Arguably more easy than what we're about to do, but that's not really the point. The point of this example is to get some practice thinking about Green's theorem, thinking about the principles involved in getting practice putting all of these different ideas together. So that's the thing to take away from what we're about to do. In any case, it might seem believable that doing this directly maybe doesn't feel like the right idea. With all that being said, let me start out by drawing a picture. This curve is a sad quartic. When x is 1 or negative 1, y is 0. So that means the curve looks like this. traveling from the point -1, 0 to 1, 0. We've seen this kind of thing before, and it feels like it would be a nice idea to use a different path. Presumably the reason why we don't want to do this directly is because the blue curve is kind of awkward in terms of the vector field. So we may be able to find a different path to consider. But the vector field might not be conservative, so we might not be able to literally use path independence. And that's okay. Instead, we can somehow use Green's theorem to accomplish this. And in terms of a simpler curve to pick, if I look at the vector field, I see a couple x squared plus y squared terms. This is always an indication that a circle isn't a bad thing to integrate over. So motivated by all of this, the first thing I'm going to do is I'm going to draw in a circular path here. In particular, I'll let C2 be the portion of the unit circle in the upper half plane, oriented from left to right. If I could somehow relate our integral to the integral over this curve, I think evaluating that would definitely be easier because the vector field will play very nicely with the red curve. But again, we'll worry about that later. Then if I'm going to use Green's theorem, the next obvious thing to do is to color in the region between them and give that a name. I'll let D be the region bounded by the two curves. Okay, so let's think about what Green's theorem tells us. It would tell us that the double integral over this region D of the curl of f, this would be the same thing as the line integral of f over the boundary curve. Okay, now here's where we're going to have to be careful about orientations of the boundary. When I write down partial d, this very specifically means walk along the boundary like this. And based on our picture, I can identify what that is with our names C and C2 using curve arithmetic. If I walk along the boundary like this, I'm doing C2 followed by -C. So this tells me that the boundary of D is C2 minus C. And then again, using curve arithmetic, we could break this up into two separate integrals. The integral over C2 minus the integral over C. The reason I want to do this is because, again, the thing that we care about, our end goal here, is the integral over C. And so what Green's theorem gives us is an equation. The two things I highlighted in purple are equal. And the idea is maybe we could compute the double integral, and maybe we could compute this integral over C2. If we can do that, then using this equation in purple, we could figure out the integral that we actually care about. So let's do that. I'll start off by considering the double integral. That means that we're going to need to compute the curl. So instead of talking you through a bunch of algebra and differentiation, I'll just let you watch me compute the curl. And so we get that the curl is 2xy times x squared plus y squared to the -2. Okay, so what we need to consider is the double integral of this function over the region D. And you might think, Joe, this doesn't really look any better. This still also looks kind of hard. Maybe we could do it, but the boundary might be a little weird with this like x to the 4th and square root of something, and then the integrand looks a little involved. You know, maybe we could do it, but it seems a little hard, and I agree. But there's a trick we can use. Now I'll let you think about it for a few seconds to see if you can see it. I can say that this integral is 0 with no computation using odd symmetry. In particular, note that the integrand, the thing that we're integrating, this is an odd function with respect to x. If you plug in negative x, you would get exactly negative that whole thing. Then the other point is, if you look at the region, it doesn't really look like it in my picture, but it is symmetric across the y-axis. So by odd symmetry, the double integral is 0. Easy. But what this tells us is that the left-hand side of the purple equation is 0. So therefore, the integral over c2 minus the integral over c is 0. So move 1 to the other side, and this tells us that the integral that we care about, the integral of f over c, it actually is the same as the integral over c2. And we showed this using Green's theorem. So now all we have to do is figure out the simpler integral, the integral over the red circular part, and presumably this is going to be easier to do because it'll play nicer with our vector field. So what do? You parameterize. Now, to parameterize this part of the circle, you could do this in a couple different ways. The way I would do it is I would call x sine of t and y cosine t. And then I want to start when x is -1 and end when x is 1. So I could let t range from -pi/2 to pi/2. Again, you could parameterize differently if you want, but you could check that this parameterization does give us that red curve. And I can compute r prime. And then set up the integral. The bounds will be from -pi/2 to pi/2. I'll plug my parameterization into the vector field. Now the denominators of the vector field are x squared plus y squared, which is 1 on this curve. That's why I picked the circle. So here's the vector field. Dot r prime. Multiply out the dot product and simplify. And we're left with the integral from -pi/2 to pi/2 of sine of t times cosine of t. Now you could just do it. Pretty easy antiderivative, but for the same reasoning as above, I can tell you already that this is going to be 0 using odd symmetry. Sine of t is odd, cosine of t is even, so their product is odd, and we have a symmetric interval about x equals 0. So again, if you don't believe me, you can just check, but it's going to be 0. And there we go. This integral that we cared about from the beginning equals 0. Kind of cool. And like I said, this is not the only way to do this, and it's arguably not even the best way to do it, but it is definitely a way to do it. And it uses some nice ideas of Green's theorem and relating to simpler curves and stuff like that. But the reality is that there's a lot of symmetry in this problem, so there's a number of other kind of quick things that you could do. But anyway, a good demonstration of how you can use Green's theorem as a tool to evaluate line integrals.